Great. Thanks very much. Maybe I just write my brief table of contents. There'll be 3 sections to this talk. The first one will be about phi gamma modules and stacks of phi gamma modules. The second section will state some conjectures. And the third section, I'll do hopefully one example, which will be GL1. And then Matt's talk afterwards, and then his talk on Monday will just hopefully have a lot more examples. So this talk will have some examples, but unfortunately we have to set up some framework before we can really discuss them. So there's going to be a bunch of definitions first. So section 1 is stacks of phi gamma modules. So I'll be quite brief about these, and if you want to see more, well, we have written quite a few notes for this. But there's also, we're going to have 2 different kinds of stacks of phi gamma modules, but one of them, what we're calling the Banach case in a minute, Matt and I taught a course in Bonn a few years ago, and we've got a survey article about those. So if you want some introduction, you might want to look at that. OK, so what's the idea of phi gamma modules? The idea is due to Fontaine, who defined them, and it's basically just to give some kind of more linear algebra-like description of p-adic representations of a Galois group. So this fix f over qp is always going to be a finite extension in our lectures. And then the idea is that some notion of a phi gamma module, I'll make this more precise in a bit, is going to correspond in some way to, it's going to be some kind of object that corresponds to p-adic representations of the absolute Galois group, Gal F, which is our notation for fix some algebraic closure once and for all and take the absolute Galois group of F. And they're going to have the feature that I'm not sure whether this was in Fontaine's mind at the time, but they also are going to have the feature that they sort of work better in families than Galois representations do. So obviously, if they were literally in bijection, that wouldn't quite be true. So what's going to be true is that they're going to be in bijection, for example, over fields, but over kind of bigger spaces, they're not going to be quite the same, and these are going to work better in families. They work well in families. And so in particular, they're going to be, when we're doing p-adic representations of the Galois groups of p-adic fields, thinking about moduli spaces of phi gamma modules is going to work a bit better for us than working with moduli spaces of Galois representations. OK, so I'll give you some actual definitions now. So for most of the rest of this talk, I'm going to take f to just be qp. I will tell you when this assumption is really needed for a theorem. Like, for the most part, all the theorems go across with kind of obvious changes to the statements. It's just that the theory is much more concrete in this case, and kind of formulas are simpler and so on. OK, so I said there are going to be 2 kinds of phi gamma modules. The first one is the case that's covered in my book with Matt, and that's, for these purposes, we're going to call the Banach case. Because it's going to be the case that when we state some conjectures in section 2, it's going to be the ones that are to do with representations on p-adic Banach spaces. OK, so so I'm going to kind of define something that's like a family of representations, a family of phi gamma modules. So I'm going to have some coefficient ring. My coefficients are going to be called capital A, and this is just going to be a finitely generated Z mod p to the A algebra for some A greater than or equal to 1. So, I mean, A can vary, so all I'm taking about is finitely generated algebras in which P is nilpotent. And then I define the following rings. I define A plus A is just power series ring in one formal variable. My variable is T. And then I can invert T and have the Laurent series ring. And this has actions of a phi and of a group gamma. And so what are these? These actions are going to be alinear. And phi of t is 1 plus t to the p minus 1. Sorry. So in other words, phi of 1 plus t is 1 plus t to the p. Let's see if I can make that a little clearer. And gamma is just the group zp star, and it's acting in the same way. So an element in here acts on t by the sort of binomial expansion, if you like, of 1 plus t to the a minus 1. So those commute, and maybe I can give a definition. So a rank D Étale phi gamma module with A coefficients is the following thing. Well, it's a rank D projective module over this Laurent series rung. So it's a rank D projective A sub A module. And it has, of rank D, sorry. Sorry? Ah! I did wonder if I should divide the board into two. And clearly I can't. I might do it on the next one. OK, thank you. I guarantee I always forget something in this definition. I thought I was forestalling that. So it's got commuting semilinear actions of phi and gamma. And those actions should be continuous with respect to the p-adic topology. So that would be a phi gamma module, and the Étale part is that the kind of linearized Frobenius is an isomorphism. So, and now I have the problem that I haven't given the thing a name, so maybe my name is M for this module, and so phi upper star M is isomorphic to M. OK, and so in theory, it's quite simple to write these things down because this group is procyclic, and so you just have to write that, choose your favorite generator, like if, at least if p is bigger than 2, so you could just choose what you want to do with 1 plus p or something, and well, sorry, a generator of fp star, I guess, mod p, and then you write down what that element does, and you write down what phi does, check that you've written down two kind of commuting matrices. Unfortunately, in practice, it tends to be a lot harder than that, but these are at least in principle quite concrete objects. And then what does Fontaine show? So Fontaine showed that if A is literally a finite module, so it's a finite z mod p to the a, it's finite as a module over there. I mean, it's an algebra, but it's literally, if it's, for example, literally z mod p to the a, then there's an equivalence of categories between these and rank D representations of the Gower group of QP. So then phi gamma modules I'm going to just not write with A coefficients, but that's what I mean. These are bijecting with the rank D free A modules with a Gower action. And then by passage to the limit, you get a statement for ZP representations and so on. And this is all quite explicit. I mean, the functor, to go from a phi Gower module to a Gower representation is you can extend to say, the bit vectors of C flat and take phi invariants and then recover a Galois action. Rather than go into that into too much detail, I'm just going to give you an example. So maybe let's look at the example of d equals 1. And I'll go back to the example that we saw in Junwen's first talk last week. Let's talk about unramified characters. So unramified characters maybe just with FP coefficients. So from gal QP to FP star, or FP bar star maybe would be better, but let's just even just do FP star. These just are given by choosing where you send Frobenius. So you send a Frobenius element to some lambda in FP star. And these correspond to, so there should be some corresponding phi gamma module. And what is that? And the phi gamma module is, so I'm going to have some generator A. So it's the module generated by, some basis vector E with trivial gamma action. So sort of A of E equals E, and phi of E is just lambda E. So it's something pretty simple. Now, again, I'm going to hark back to Junwen's talk, or also, if you want to see this example in more detail, it's, I think, in the first lecture of my notes with Matt, this survey article about phi gamma modules and stacks thereof. We saw in Junwen's talk that this thing, if I now try and consider some larger ring, like maybe I now want to take A to be sort of a GM or something, so I take FP X inverse, there is not, there's no kind of character of the Galois group sending a Frobenius to X. I can't, sort of doing Frob P maps to X in A star. This is something I'm not allowed to do. I mean, just because the kind of unramified Galois group, the absolute Galois group of FP, is a copy of Z hat, and I can't raise X to non-integral powers. On the other hand, in this phi gamma module world, this is perfectly fine. I can just write exactly the same definition and just put an X here, and there's just no problem. So there is a phi gamma module, so sort of phi gamma module taking, again, same kind of formula. This is a perfectly reasonable Étale phi gamma module of rank 1. So this is some instance where the phi gamma modules work better. Yeah?
So there's that question. How can the phi gamma modules know about the Galois group of F when the definition doesn't depend on F?
Yeah. So this should have said QP in this case. The point is, so yeah, sorry. In general, there's basically a very similar definition. And in fact, what changes is that the formulas for the phi and gamma actions are more complicated. But yeah, thanks. Yeah, the field F is fixed and is QP at the moment. Any other questions?
One more while I'm at it. So the action of phi seems like it's the same thing as gamma except for P.
Yes.
So is this the same thing as just that action but for the full multiplicative monoid?
Yeah, so...
Toby, can you repeat the question?
Yes, so the question last time was like, why does this say F and not QP? And that was the answer. It was more or less the question. This time the question is, could we think of this as being an action of sort of QP cross instead of this separating this phi and this gamma? And the answer is yes. I think that's something that's a bit more peculiar to the fact that we're thinking about QP, and this is somehow goes in, or maybe someone will say something epsilon about this later, but somehow that interpretation does come up a lot in Colmez's work on p-adic Langlands, but I'm not sure. I don't think I can say something more than that. OK, so in some sense, on the other hand, this fix here is doing the same kind of thing. So Hellman's talk, he had a different fix for this issue, which was instead of thinking about the Galois group, you just think about the Weil group, which again has this effect of you only have to consider integral powers, and so that was great. So it turns out that for rank 1 representations, I mean, he was in an L not P case and we're in an L equals P case, but for rank 1 representations, you can check that in fact these things are, and I'll hopefully do this in the GL1 example, these things are actually also just equivalent to representations of the Weil group. But that's misleading, and I think it was promised by Hellman that I would say something about this here. So for rank 1 things, that's fine, but for rank 2 things, it's not the case that these are the same as representations of the Weil group. So let me just give you an example. If I consider, let me just write something and then explain the notation. So this is some notation for a 2-dimensional Galois representation. So unramified lambda is the unramified character of Gal QP, sending the Frobenius at P to lambda. And this is some extension. And then if alpha and beta are in, say, let's just say they're in FP bar cross and alpha is not equal to beta, then just by kind of Tate duality and Euler characteristic formulas, there's a unique non-split extension of these characters. There exists a unique non-split extension. And you would certainly imagine that if I now kind of imagine varying my alpha and beta and just allow, I've got these non-split extensions that I can just vary those as well, that sounds like some reasonable family of representations that you might want to exist. So then what happens is that there does exist a phi gamma module kind of realizing all of these extensions, all of these representations. But there does not exist a reasonable representation of the Weil group doing this, some universal representation. And the basic issue is that if you allow alpha and beta to vary completely, then the subgroup of the wild inertia that's cut out by the inertia up here is not some open subgroup. So this is some kind of contrast to what was happening in the L not P case, where we kind of got to truncate the wild inertia somewhere. Here, I mean, if you fix the field that these lie in, then there's only there's only a finite amount of ramification. But if you really vary over all possible choices in FP cross, you can just check, like some explicit actual calculations in class field theory or something. You can check that you're going deeper and deeper and deeper in the ramification, and you can't make some nice family in a reasonable way. Okay, that's about as much as I wanted to say about that. Let's see if I can swap some boards around. Probably I should get that one down. Okay, let me not swap around too much more than that for a second. So
the phi-gamma module that you're talking about there would be again over some ring of the form FP.
Yeah, like X, Y, X inverse, Y inverse.
Alpha beta, right?
Yeah, so the question was what kind of family, what kind of ring is this over? And I guess it's like, if I'm talking about a family that parameterize these things, I guess I want to have like a product of two GMs and delete the locus where they're equal, which I was starting to try and explain as a ring, but that's not a good idea. But yeah, you can just build a phi-gamma module explicitly over that in some real sense, because there's an explicit kind of formula for the corresponding X group. But yeah, let me not do that right now because I'll never get anywhere if I do, but it's definitely a fun kind of exercise to try and make that quite concrete. I should also just say that the precise definition of these Phi-Gam modules, I quite like the fact that you can write it down in this way, and it is useful in some proofs. But there are a lot of other descriptions, equivalent descriptions of this data that can be given. You can do things like modules over vectors of C flat with some, or yeah, vectors of OC flat with some extension of coefficients, and there's probably some version with prismatic F crystals and so on. But these are all going to be kind of equivalent things, and for the purpose of the rest of the conjectures and so on, really what matters is that there's something that on, for example, fields like on FP bar or something, they do agree with Gauss representations, but they just behave well in families. That's kind of the key thing to take away. So the definition of the first stack that we're going to have. So I should draw attention now, there's going to be two different kinds of X's in this talk, and this is a calligraphic X. And I hope I've got two different kinds of handwriting lined up, but we'll see. So I'm going to tell you what this is going to be some stack that I'm going to tell you what its functor of points is. And so this is just the thing I was just defining. So this is the groupoid of rank D projective. Forget what that's supposed to be in the definition or not, but étale Phi-Gam modules with A coefficients. And this is a groupoid, so it's just, by definition, the morphisms of the isomorphisms. And so then the theorem, which is most of the theorems in the book that we wrote, is that this is a Noetherian formal algebraic stack. I guess over ZP. It's over ZP by definition. I should say it doesn't have the p-adic topology. It's kind of more formal than that. And the consequence of that is going to be I'm now going to tell you a little bit about the underlying kind of reduced substack, and then about the thing itself, and you're going to see a bit of a difference. So the underlying reduced substack is equidimensional. Of dimension equal to d times d minus 1 over 2. So this is the dimension of some Borel, or maybe, sorry, of some G mod B, I guess, some flag variety. And furthermore, there's an explicit enumeration of the components and a description of them in terms of the representation theory of GLD of FP, which will maybe come up a bit in GL2 case in Matt's talks. And kind of thirdly, I'm going to put this one slightly in parentheses because it's not quite maybe proved, but I'll say why. This is the whole stack is LCI, and I guess equidimensional of dimension 1 plus d squared, and it's also actually flat over ZP. So the reason I put this in parentheses is I'm not sure that all of these concepts have actually been defined anywhere for Noetherian formal algebraic stacks, but this statement is true for the versal rings and was proved by Berkler, Iengo, and Proskunis. And perhaps I should say, what are the versal rings of this stack? Well, basically by definition and by Fontaine's theorem, they're the same as Galois deformation rings. So what are the points of this stack? The points are just like, the FP bar points are just representations valued in GLD of FP bar, and then the deformations of those, well, you deform to Artinian rings, and then Fontaine's equivalence applies, and you just get back Galois deformation rings. So this is some kind of, the picture is very similar to the kind of picture in Xinwen's talk, where if you kind of literally write down moduli of Galois representations, if you write down this thing, you have something that's maybe like a kind of smooth family. But the kind of relationship to Galois things is that at each closed point, you have some sort of formal things given by the Galois deformation rings that don't communicate with each other. I can see lots of blank looks, and I feel tempted to give a lecture about that instead, but I'm just going to, that's all I'm going to say about this. But again, I think the first lecture of these bond lecture notes that I mentioned explains this with some pictures even. Okay, so that's all I wanted to say about the Banach case. Maybe I should see if there's any questions before I do the analytic case. Okay, so
What do you mean by Banach?
so there's going to be two things. There's going to be something called Banach and something called Analytic. And the terminology is going to be coming from the representation theory side. So these are going to be like the parameter spaces, like the parameters, these are like the moduli spaces of L parameters. And they're going to, some sheaves on them are going to correspond to some representations. And the representations will have those names. So hopefully it will become clearer in the second section.
Okay, can you make precise what you mean by like this ID is related to Galois formatory? So in that case, you are taking out coefficient to Galois.
No, so I literally mean, yeah, so sorry, I'm I'm going to try and put it in context, but thank you. So a point of this thing is just a map, say, from like spec of FQ, which is some finite extension of, this is like a finite extension over FP, mapping to my stack is the same thing as, this is the same data as a representation. Sorry? Thank you. I went wrong very quickly there. Thanks. So this is the same thing as a representation to GLD FQ. This is literally what a point is. And then versal rings at this point are literally given by the usual unrestricted, like framed Galois deformation rings in the sense of Maser. So it's really literally those. And that's basically a consequence of the definitions and of Fontaine's theorem.
Naive question. How could the reduced dimension have less reduced dimension?
Yeah. So I mean, the point is like it's just like if you, how can the reduced dimension be smaller? It's just like if you imagine that I'm looking at the formal scheme like FP double brackets T or something, and then the underlying, like that's maybe some one-dimensional thing, and the underlying reduced is just a point.
Get rid of this formal stuff.
Yeah. So it's a little confusing, the terminology, but so there's like an algebraic, that thing there is actually, and that's like an algebraic stack. So you have these algebraic families of like roughly half dimension, and then a lot of formal directions.
Do this Galois representations kind of have this dual behavior also?
So Jared is asking if the Galois representations have this kind of behavior as well, and the answer is basically yes, but it's less visible. I mean, one explanation for this is that in some sense, I mean, I'm not sure if this is a real mathematical explanation, but one way we see this is that you can find sort of families of this size, genuine families from sort of crystalline representations. And somehow if you could find bigger families, when you do various calculations, you would find that you had like infinite dimensional spaces of modular forms or something. If you think about the interaction between global, this will be more in Matt's thing as well, but there'll be interaction between these local things and global spaces of parameters. And somehow if you have very large algebraic families in this local setting, you would also have large families in the global setting that were too large. And in particular, I mean, there's some constraints, at least morally, from spaces of modular forms being finite dimensional. But sorry, I feel like I'm saying answers that might be helpful if I expanded on them for half an hour, but that's some kind of principle. Okay, well, let me be very brief in my introduction because I'm spending far longer than I should be, of the analytic notion. But again, so these are called analytic phi gamma modules. And so these are going to be the ones that come up when you study things like eigenvarieties or triangulin representations. And they're relevant for the sort of locally analytic representation theory of p-adic groups. So here is where I'm supposed to start using this other x. Unfortunately, I think in talks, this is usually what I use for this, which is a bit of a disaster, so I'll probably get it wrong again. But so this is a rigid analytic stack over QP. And its points on aphanoid rigid spaces are just kind of the same thing, rank D phi-gamma modules. Not necessarily a tile now. You might see that in the GR1 example if we ever get there. Over a ring that I'm not going to define, but I'll just give some notation if you've seen it before. So this is the robber ring. So if I had another 5 minutes, I could, again, give some explicit definition of this thing. It's like some ring of power series that converge on some annuli, and there's, again, explicit formulas for phi and gamma. And I'm told that much of the audience would prefer if I said it was Galois equivariant vector bundles on the Farg-Fontaine curve. So that's another way of putting it. And there's, I think if you look in the notes, there's maybe like 8 different equivalent descriptions of this category if you want to see lots of them. But then we don't yet have a theorem. There's just a conjecture that this sort of has some similar behavior. So it should be a rigid analytic R-twin stack this time of dimension, equidimensional of dimension d squared. So one less, just because there was one dimension there that was just the ZP direction, and we've inverted P. And it should be LCI and normal. And the expected relationship is to this one is that there should be some, again, this is all part of a conjecture. So there should be a map from the rigid generic fiber, I think we're just calling that rig, to XD, which should be formally a tile. So this is not a representable morphism. Roughly, this stack here is kind of a stack of sort of ZP representations, so it knows about lattices, and this is maybe some stack of QP representations, and so there's some aspect of forgetting a lattice. And it's also very far from surjective because, I mean, I'm not going to get into this, and if we do GL1 at the end, I can show you very explicitly, but phi-gamma modules here, and if you've seen triangulating phi-gamma modules, you'll know there's lots of interesting non-atile phi-gamma modules, and all the things coming from here are atile. So the geometry of this is not what you might naively guess. Yeah, the image is sort of, in this vector bundles on Farg-Fontaine curve, it's the semi-stable slope 0 things. OK, that's about all I want to say about the analytic case, which unfortunately, there's a lot in the notes, but in the lectures, we're kind of somehow ending up prioritizing the Banach case, and I apologize. That's the end of section 1. Are there any questions before I do some representations? Yeah. The atile part there was actually the part that the linearized Frobenius was an isomorphism. Now that was also, I mean, it's a bit misleading because here the linearized Frobenius is also supposed to be an isomorphism. The basic difference is that when you're over QP, multiplication by P is an isomorphism that you're allowed to consider. And sort of atile things will be avoiding that, and you'll be multiplying by p-adic units instead. That's kind of like the rough flavor of what the difference is. Yeah.
So your formula makes sense for general adic space and analytic adic spaces, or is it something about rigid adic spaces?
At least for me, I think I just want to be defining things literally on aphanoids, and maybe we can ask Eugen later if there's something much more general, but my expertise runs out exactly on what I've written. So, OK, so let me try and actually have some conjectures. Maybe I should make some use of this board. OK, so again, I'll start in the Banach case. So I need to make some definitions. So some more notation. Start Banach.
So the XD rig is known to be normal?
Is this known to be normal? I certainly expect it. I don't. I mean, right. Yeah. So as Eugen is saying, that's basically roughly what I was going to say as well. Like, I always have to pause a bit because I'm not sure there's any kind of great general theory that we have access to discuss these questions. But for the versal rings, you can ask the same question for the generic fibers of the unrestricted local deformation rings. And again, Berkler, Jenger, Pascunas have proved those are normal. So I think all the properties are known for the deformation rings, but it's probably, yeah, exactly. But that's not enough information. And
I mean, isn't there going to be like a semi-stable component and a crystal component?
But that's, they've got high codimension and...
I don't know, maybe put it through then.
Okay, so maybe there's some debate about what's known for deformation rings, which we can come, I mean, I don't think having a real-time discussion between...
Maybe it's some semi-stable plane, I'm not sure if that's one.
Let's come back to this in the next lecture, maybe. Because I don't think, at least I'm not going to be usefully resolving this question in real time. Okay, so let's let G denote GL. So now I'm going to just let kind of F over QP be a general finite thing. For the moment, and just because I'm going to say some things that are independent of anything. And K is my notation for the maximal compact. GL2. OF. And again, I mean, there probably should be versions of everything we're talking about, not just for GLD, but for general reductive groups, but we don't even have definitions of the stacks and so on, so it seems best to kind of keep some notion of where we are and just stick to GLD. So definition, I want to talk about some kind of completed group ring for G. So this is some slightly non-standard notation, but this is just, by definition, you take the group ring for G and you tensor over the group ring for K with the usual completed, so the Iwasawa group ring for K. So this is just the usual inverse limit of the finite group rings where you run over open normal subgroups. So from the definition, it's not maybe not immediately obvious that this is actually a ring, but in fact it is, and it's easy to check just by the commensurability of compact open subgroups that the obvious multiplication on this makes it a ring. And the reason for doing this is somehow the kind of modification, it's convenient to make this modification of the group ring of G to talk about, think about smooth representations as being modules over some kind of group ring. This is the kind of group ring that acts. And I will use occasionally that you can identify this group ring with its opposite by just the involution of G going to G inverse. I'm going to use that kind of without comment, but basically at some points there'll be some left modules turned into right modules, and that's how I'm doing it. Okay. Maybe I'm actually just happy to get rid of the analytic case immediately. Okay. And so, as I was just kind of saying verbally, so smooth representations of the group G on Z mod P to the A algebras are naturally left modules over this completed group ring. And that's often a convenient perspective to adopt. We're going to, I mean, basically what I'm skipping, I mean, so I haven't motivated this at all. What I'm going to do is define some kind of derived category of representations and then speculate that there's some functor from it to some sheaves on some stacks. And to define an appropriate category of representations, it's often doing some kind of homological algebra. It's kind of convenient to have some access to thinking about modules over rings or something. And so that's the reason to do this. And indeed, there's an immediate definition of finitely presented. smooth representations are by definition those smooth representations which are finitely presented as modules over this group ring. So that's going to be some notion that's useful for us. So finitely presented just meaning a co-kernel of finitely generated modules. And then we have a first conjecture is that I'm going to call smooth G FP. So this is the category of, sorry, this is appalling, but this is the category of finitely presented smooth representations. The conjecture is that this is abelian. So the substance of this is that if you have a morphism of two such things, that the kernel is also finitely presented. So this conjecture is known at least for GL1, which is easy because in that case, this ring is even just an Ethereum ring. And it's known for GL2, sorry, PGL2 at least, by work of Jack Schotten. We hope that and suspect that it's true more generally, but I'm not sure that it's a question that's been that much thought about in the literature. Okay, but I'm going to omit that conjecture from now on, but the fact that we know it for PGL2 is going to mean that, and most of the examples we're going to talk about are basically going to be for PGL2, so it's not an issue there. And then, probably I should fetch that top board down at some point. I can actually, this is not, I think leaving it alone was actually working better for me, but okay. Okay. So I'm going to use that conjecture now. And sure.
Does this ring ZP double bracket G depends on K? Or?
No. So the question is, does this depend on the fact that I chose this compact open? You can choose any compact open, and there are comparisons and canonical isomorphisms, and it's a nice, yeah, good question. I mean, in some sense, the exercise of proving that and the exercise of proving it's actually a ring are closely related. Okay, so where was I? So I'm almost ready to say the actual main conjecture of this thing. So let's let D be, it's probably not right in the shadow, D be FP of smooth G is the category of bounded complexes. So it's some kind of, I mean, as the notation suggests, it's supposed to be some bounded derived category of finitely presented representations. And so it's bounded complexes of smooth G representations, all of whose cohomology groups are finitely presented with finitely presented cohomology. So one can check that that's some reasonably well-behaved thing. And then we have a conjecture. Sorry, I can't hear it. Yeah, I think that's a correct. That question is that the same as bounded complexes of? Sorry, now I've forgotten what the question was. Is it the same as bounded complexes of smooth? Yes, exactly. Whose cohomology is finitely presented? So smooth. Yeah, there's a. I think this is addressed in Appendix B now, but it might not be. Appendix D, I'm told. Yeah, there's various.
With a citation to Appendix B.
Yeah, okay. So yeah, we spent a little more time in these notes than to satisfy ourselves that we were not just making nonsense definitions. And I think this is equivalent to any kind of other definition you want to give, as long as you admit this conjecture. And otherwise, if this conjecture is false, then this is the wrong definition, and one has to find the right definition. Okay, so the conjecture. Yes.
Yeah, so if I'm given like random percentage, it's kind of modules, do I automatically know it's a smooth representation, so it's not automatic?
The question is, are finitely presented modules over this ring smooth? Right. Yeah, so the important example is like, yeah, the ring, it's not the case that all these, the finitely presented modules are these smooth representations, because just, I mean, an example we'll see in a minute, the group ring itself is very far from being an object in this category.
But
Some kind of,
very easy to identify which capture.
Yes.
yes.
Imagine there's like ZP modules, and then you have ZP modules that are killed by a power of P.
Yes. So yeah, Matt's saying the good analogy is ZP modules and ZP modules killed by a power of P. And that's the case of like maybe where the group is the identity, the trivial group. Okay, so let me actually make sure I do state a conjecture. And I think I had a reference. So this is like, I'm going to give you a reference to the notes because there's a lot more. I'm going to state it very briefly, and there's a lot more details in 616. So there exists a fully faithful co-continuous. So for me, co-continuous means preserves co-limits, which I think is what geometric Langlands people call continuous, but we call it co-continuous. ZP linear functor.
So maybe you don't want to say co-continuous if you're on the DP.
What would you rather I said?
It is co-continuous in a way to describe the extension in.
Yeah, okay. Let me say ZP linear, and then, yes, I see your point. Thank you. Yeah, thanks. Okay, smooth. From this category to the bounded derived category of coherent sheaves on this stack XD. And then similarly, we extend to a co-continuous functor. I mean, these are the compact objects, and you can extend to D kind of in categories on each side, if you prefer, but we mostly will keep in examples in just these finally presented things. And it's going to have some properties, and just swap these two maybe. So such that, some object we'll see a bunch of is L infinity is what happens. So unfortunately, I'm now going to write down something that doesn't make any sense. So this is some kind of frac A symbol that I'm not doing a job of drawing. You can make sense of evaluating it on the group ring itself, which is some kind of pro object. And this is an actual sheaf. So I guess it's like a pro-coherent, or maybe if I knew what I was talking about, it would be some kind of solid sheaf. But it's concentrated in degree 0. And it's flat. It's not flat over it's a module for the group ring again. But it's flat not over the group ring itself, but over the OSR algebra of the maximal compact. And so from that, you can deduce a kind of formula that this functor for anything is just given by taking derived tensor products against this L infinity. And so in particular, this functor is necessarily going to be right T-exact. So really writing down this functor, which sounds like something kind of abstract, in some sense is just a question of writing down some kind of sheaf of representations over the stack, and then you just take, it's like that's the kernel for your functor. And then we expect that a few more properties. So we expect that it has amplitude I think 1 minus d to 0. So in the GL1 case, it literally gives you something on the underlying abelian level, and for GL2, it kind of shifts things possibly 1 degree to the left and so on. We expect that in the kind of situation of Taylor-Wiles patching, and I think Matt will actually say something more about this in his talk in half an hour. But I can use some kind of similar notation to Eugen had. So there was some kind of ring R infinity, and that gives you some versal ring at the stack. Then if you pull back this L infinity, you get M infinity. So what is this M infinity? This was this kind of patched representation that appeared at the end of Eugen's talk, and as I say, hopefully will appear again in Matt's talk. And I should say that, I mean, these notes we wrote were very long, but just after this conjecture are a series of remarks that will hopefully spell these things out in detail, and I think are quite readable. Maybe the other thing actually I want to just advertise about our notes while I'm advertising them is the introduction, I think, should be genuinely readable by everyone and hopefully gives more motivation for the things we're doing. So I do, invite people to have a look at that. I mean, feel free not to, but it was definitely written to be readable by everyone here. So there's a compatibility of some kind of duality. So let me just say you take R Homs over the group ring to itself and some Grothendieck-Serre duality, appropriately modified as in Jim-Wen's talk. And there's a statement about what happens for locally algebraic vectors. So one way of saying that would be if I take the compact induction of something I could call V lambda. I don't quite remember what Eugen's notation was, but this is just some representation of algebraic representation of highest weight, something to do with lambda, off by a row shift, that this should be supported on some appropriate crystalline locus, which I also am not defining. So this is just in much more down-to-earth terms. So this expression here, maybe I should also say, this is some kind of local global compatibility. This patched module is something that was ultimately constructed by glomming together the cohomologous and Shimura varieties at some levels. And so this kind of statement here is coming down, and again, this will be hopefully explained more in Matt's talk in a minute, but this is, in the end, coming down to saying that some spaces of modular forms of some weight, that the associated Gauss representations are crystalline of some specified weights. So this is, in the end, this is motivated by some quite concrete statement, if you regard that as a concrete statement.
Okay, I'm profoundly confused about this.
Brilliant.
L infinity, I mean, I understand it doesn't literally belong to D co.
Yeah.
But nonetheless, your comment about it being over ZPK, I'm expecting something more like a phi gamma module, but you're saying it's actually lives in the first category.
So let me try and answer the question while stating it. So L infinity is similar, you should think it's a sheaf of representations of the group. So it has the structure as being some huge sheaf on our stack, but it has an action of the group.
So I think you're using...
Sorry?
It would be like flat over OXD brackets K.
I mean, yeah, but I think it's also just flat over ZP brackets K. Am I wrong?
So
Do you understand my profound confusion, though?
I mean, I think your profound confusion was you were expecting me to say something more about it being like a phi gamma module or something.
Yes.
But it's a coherent sheaf on a stack of phi gamma modules that has an action of a group. And I'm just thinking about its avatar, like the fact that it's a representation, in particular it's a representation.
To say is that when ZP double bracket G is a ring R, so it's an R module, but the endomorphisms of that particular R module are the ring R.
Yeah. Okay.
So this is a functor. So when
Yes.
you apply the functor to it, the endomorphism, and it's even supposed to be fully faithful.
Yes. Let me say some of these things into the microphone so everyone can hear. But the point is that this is a fully faithful functor I'm feeding in something that has endomorphisms, basically this ring. So the thing that comes out also has those as endomorphisms. So this thing is a sheaf, but it also has this canonical action of this. And in particular, I can restrict, and it has an action of this, and I'm just saying it's flat. And so the motivation, again, the motivation for that, perhaps, for the imaginary audience member who's happy with everything apart from why I'm making that statement, would be that when you pull these back and have these completed cohomologies, the completed cohomology groups are just flat over the Iwasawa algebra, which again, I think maybe was actually even in Eugen's talk. And that's some motivation. Sorry, every time I talk about this seems to generate some huge confusion about like the fact that this object here, I mean, because we're feeding in such a big object, it has these endomorphisms as well. So it kind of, this L infinity has everything. Like it's some universal sheaf of representations of the group. And so then that's, I mean, this formula here is kind of tautological in some sense.
Well, it sounds like you had to construct L infinity first.
Right, so if you have a function, yeah. So how would you ever prove such a functor existed? Either you would do some kind of thing like maybe like Farg-Schulze would do and do some kind of great construction, something comes out and you've got a functor. The other alternative is that you could try and write down an L infinity. I mean, maybe I should get to the end of these and I can state a theorem and that will be about having an L infinity and then we're going to run out of time, but let me maybe try and get that far. So I just wanted to say, because I guess what I'm going to completely fail to do, I'm afraid, there's a parallel version of this conjecture. So maybe I'm just going to do the kind of emergency maneuver of seeing where I should refer you to. So there's an analytic version of this, which is conjecture 6.2.4, which will be some parallel version of all this in the analytic setting. And when you're in the analytic setting, there's also a recipe for what happens when you take this sheaf and pull it back to the analytic generic fiber. You can actually explicitly say what it is. But the question of what these sheaves are, these sheaves have the kind of things that come up a lot in proofs of modularity and so on and are quite mysterious. But the rigid generic fibers you can specify. The other thing I wanted to say is that this duality combined with this, you can use to show that these sheaves actually have to be maximal Cohen-Macaulay, which is the kind of thing that comes out from the patching method. There's also supposed to be some compatibility with parabolic induction. And that's in the same kind of way as in Xinwen's talk, where you had the stack of torus, Borel, and the group, and you do a push-pull type thing. And again, that one's particularly important actually in the analytic setting. Okay, so that I don't just completely fail to communicate anything, let me just try and now state what's known about this conjecture, which is not so much. Sorry, give me 1 second. I don't think I can handle the boards and maths at the same time.
What's V lambda?
V lambda, so yeah, sorry. Let me just do GL2. V lambda might be like, it's a representation of GL2 ZP, say, if I'm doing GL2 over QP. And it's just like the nth symmetric power of the standard two-dimensional one. And then the X Chris lambda would be the locus with Hodge-Tate weights, crystalline things with Hodge-Tate weights 0 and m plus 1. So in general, it's just some Weil module, and there's a row shift to get the crystalline, get the weights of the Gauss representations. You could put in more general coefficient systems as well. There's a version with a type or anything. And then where they're supported is what's predicted by the local Langlands correspondence, the kind of more classical local Langlands correspondence. Okay, so what's known is, well, section 3, that's not going to happen, but if people have, I'm not going to make Matt do it, but if people want to ask about it later, we can say something about it. So for the GL1 case, it's known. And then kind of, I should say expected theorem, but we're kind of some way into writing it up, is that if P is greater than or equal to 5 and G equals GL2 of QP, I will put the names and everything, but yeah, let's not. Yeah, G equals GL2 QP, and we consider the case of fixed determinant, then yes, it's a theorem of Andrea Dotto and Matt and me. So fixed determinant, you could just do PGL2, but you can work with any setting where you just fix central character, yes. Central character on the representation theory side and determinant on the Galois side, thank you. So then the theorem, the conjecture holds, and what's the proof? Well, the proof is that, this is not at all the proof, because the proof is going to be really long, but L infinity is what's called d-natural box P1, which is something that Colmez defined a long time ago. I mean, he defined it in a much more special setting, but if you kind of read all of the kind of original proofs of p-adic Langlands for GL2QP, the kind of more classical p-adic Langlands, you can find something that turns out that does exactly have, it does play the role of this kernel. So this kind of, also for GL1, I mean, it's in this sense, you can just explicitly describe the stack, everything's easy, and the structure sheaf turns out to be the L infinity, and it's all kind of trivial. In this case, you can explicitly construct this thing by some very mysterious argument using phi gamma modules. But I'm a minute over time, so let me stop.
Any quick questions? Okay, so maybe I'm just a little bit too young, but what is finally presented in a condensed setup?
What is finally presented in the condensed setup?
I feel like all of these things should be naturally condensed, right? And then should in a way be able to say what that means.
I'm sure someone should be able to answer a question. I'm not going to try and answer a question about condensed mathematics on video right now. So maybe the Q&A session. Yeah. Yeah, so I think the question is there like an abelian version where I can just take smooth G and do it? Not that I know of, although I think you can already ask that question in the L0 P case, and I think people have started to think about that. I mean, ultimately, of course, one hopes that there should just be some version that's more like the picture in Peter's talk, where there's some kind of equivalence, and then you can look at different T structures on both sides, but you'll have to enlarge the category of representations. And when you've only got fully faithful functors, it's a little more alarming to rearrange things on too much. But yeah, it's an interesting question. I think for GL2QP, I kind of expect that this has an affirmative answer, but I've not tried to check the details. Yeah. Sorry, you're asking if the XD is a substitute for a... So exactly. So the question is that does this have this XD has something to do with like the stacks of L parameters in Xinwen's talk, and it's exactly the L equals P analog in the case of GLD.
This thing has kind of also integral structure somehow.
Sorry, it has.
This thing has integral structure.
A what?
This is like a problem.
Yeah. So yeah. Okay. So the other difference is that in the L not P case, you just have some locally affine type scheme mod some reductive group here, and here we generally got these formal directions. I mean, maybe in each case you can kind of think that the whole thing has some kind of in structure, and in that, if you want in the L not P case, you could think about the kind of letting the conductor grow as some kind of in thing, and here the in structure is a more formal one, kind of moving away from the crystalline directions or something. But it definitely makes this thing behave quite differently from the L not P case. I mean, you will see some examples in Matt's talks about actual geometry of these things.
Okay, so I suggest we save the other questions for the Q&A session and thank Toby again for